Alright, so this first video is going to focus on the different types of bonds you can have, ionic and covalent. We've talked a lot about ionic compounds and covalent compounds already. That ionic bonds are what we find in our ionic compounds, and they form when electrons are transferred from your metal to your non-metal, or your cation to your anion if you're dealing more generically with polyatomics. And these will always result in a polar bond because you will have your anion that will have a full complement of valence electrons, while your cation will have no valence electrons in the atom's original valence shell. Coulomb's law is a way to quantify how ionic an ionic bond would be. You have that constant there, and I'm not going to make you do this calculation, so I'll give you the equation on any sort of assessment, but you will not use it to calculate a value because we're really not going to focus on the radiuses as much, but you do know about the radii from what we've just talked about in with periodic trends. Q1 and Q2 are your charges, and because your cation's charge is positive, your anion's charge is negative, that value will always result in your energy of interaction with Coulomb's law. It's called lattice energy for a pair of ions to be negative, which means energy would be released. It's an exothermic change. So the value, what you need to know about Coulomb's law is that basically the greater that charge product, the greater the charge ratio is between your cation and anion, and the smaller your atoms are, the more energy is released, the more likely those two elements are to form an ionic bond. We're going to spend a lot of time on covalent bonds, so I'm just going to briefly touch on this. You've already seen a lot of this in the lab we've been doing. This is when we share our electrons. This happens to be a non-polar covalent bond because the electrons are distributed equally between the two chlorine atoms, but we will also have polar bonds where the electrons are not shared equally. Electronegativity was something we talked about in your first chem class. Electronegativity is basically a measure of that element's ability to gain a pair of electrons. And our noble gases, since they already have a full valence shell, do not have electronegativity values assigned to them. Fluorine is your most electronegative atom. It wants electrons the most. It's the smallest, which means the nucleus is more aware of what's happening with that valence shell than with any other element in row 2, and it has one valence electron away from a full shell, while francium is one of your largest atoms, and it would have the smallest electronegativity because it is much further away, its valence electron, from the nucleus of that element because of the field energy levels between it and the nucleus. And so it would have a much smaller electronegativity value assigned to it. So short story, electronegativity increases going across and decreases going down a group. Noble gases, again, are not assigned electronegativity values. So the further apart two elements are on the periodic table, typically speaking, the greater the difference there will be in their electronegativities, and typically the more ionic bond will form. So this is a table of electronegativity values. I will not expect you to know this table of electronegativity values, but if I ask you to do something with such a table, it would be provided for you. You can see there fluorine has the largest electronegativity value assigned on the Pauling scale. These do not have units, 4.0. While if we look down at cesium, it's at 0.8. I want to say francium is like 0.7. Okay? So what we're going to do here is look at pairs of ionic compounds to determine which one would have the greatest lattice energy according to Coulomb's law. So we want to basically look at the two compounds that I give you, compare their charges, compare their sizes, see which factor we're looking at. I won't ask you to try to compare more than one factor at a time. So with KF and KBr, they both have potassium, which has a charge of +1. Fluorine and bromine are -1. So it's not the charge product that's going to have an effect, but it's the atom size. So fluorine is a little smaller than bromine, and because of that, that would have, because you're dividing by the radii, that would give you a larger lattice energy. So Kf would be the compound in this set that has a greater lattice energy because of that smaller radius. And our next one, we have magnesium chloride and aluminum chloride. This time we do have a charge difference. Magnesium and aluminum are in the same period, so their size, they're right next to each other, is going to be roughly the same. Magnesium is +2 and chlorine is -1, so that gives us a charge product of -2. Aluminum's a charge of +3, chlorine's a charge of -1, that gives us a charge product of -3. So the aluminum chloride compound would be your best choice because it has a greater charge product than MgCl2. And letter C, we have BaI2 or Al2p3. Barium is closer to, barium is closer to francium than aluminum is. Iodine is also fairly large, so those are two really big elements. So they're going to form larger ions. Aluminum and phosphorus are higher up on, or are earlier on in the periodic table, which that means their radii are smaller. So right there we've got the radii part taken care of, and then we also have the charge issue. So if I do ask you to look at both factors, I'm going to make it so both factors lean the same direction. Right now, the barium iodide compound is bigger than the aluminum phosphide compound. The charge product for barium iodide would be -2, barium's +2, iodine's -1, while aluminum is +3, phosphorus is -3, so it would have a charge product of -9. So it wins on both factors, and it would have a greater lattice energy as a result. And I want to say, we think we've got a couple with electronegativity, and then that's it for this video. So we've got sodium, potassium, and rubidium. If you look on your periodic table, you're going to see that sodium is the highest of the three elements in the alkali metals, then potassium, then rubidium. Again, as you get closer to francium, you're decreasing in your electronegativity value. So rubidium would have the least, sodium would have the greatest, and potassium would fall in between. With sulfur, oxygen, and fluorine, sulfur is actually in period 3, but it's in the same group as oxygen. Fluorine is your most electronegative element, so we know it's going to be on the end. Because sulfur has that filled energy level separating it from oxygen in terms of the nucleus and its valence electrons, sulfur would have the least, then oxygen, then fluorine. Okay, and the last one I'm going to have you look at, I believe, is BF and BCl. I want you to predict which bond would be more polar. So if we're looking to see which one would have a greater distance between the two elements, BF and BCl. And I think if you look on your periodic table, you're going to see that BF is more likely to be polar, just again because fluorine's so electronegative. And there's a couple ways you can tell me which one's the negative and positive pole in the bond. Boron is always going to be the more positive when compared to fluorine. Your halogens are very, typically halogens, fluorine and chlorine, as well as oxygen, are very electronegative. The closer you are to fluorine, the more you're going to want to hold on to your electrons. So fluorine would be the more negative end of this bond. Another way you could write it would be to use an arrow pointing from the positive boron to the negative fluorine atom. And then you can use a delta sign to represent a plus for the positive side of the bond, and a delta negative to represent the negative side of the bond. And I believe that's it for the first video. So that should get you to your first worksheet.